Okay, welcome also to the people who are watching us on the YouTube live stream. We'll get started in 1 minute. Okay, I think we're good to go. Evan, if you're ready.
Sure.
All right, so welcome everybody to this, the fourth EasyBuild Tech Talk, this time on AMD Rome and Milan, by Evan Burness from Microsoft Azure. So the floor is yours, Evan.
Sure. Thank you for inviting me. I appreciate it. To everyone who's joining in, watching live, I know it's late in the day for some of you or very early, so wherever you are, thanks for joining in. I was asked to come and talk a little bit about some thoughts we have on AMD's Rome and Milan processors for high performance computing use cases and our experiences. And I said, we'd be glad to. So that's what I plan to spend most of today's time on. And I titled this sort of a part one because I sort of agreed with the EasyBuild organizers that if there were follow-up questions, if there was more content, or that people wanted me to go deeper on, or if there were areas I didn't cover they wanted me to do to speak to, I'd be happy to come back and do something additional. So just consider this sort of an opening salvo. Here's what I really just want to do today, which is since there's a wide range of HPC folks out there in different kinds of roles and with different levels of awareness about AMD EPYC, or even just infrastructure for high performance computing as a general matter, different stages of either buying or investing or using EPYC for high performance computing, just sort of wanted to do a sort of like a discussion that was sort of good for all of these kinds of audiences and walk everyone through these things, because whatever stage you're at, there's a pretty good chance that I and the broader team at Azure have been through that before. And we'd love to just sort of share what we've learned. And if that provides benefit to you all, that'd be terrific. So like I said, I just call it, what's all the fuss, talk through some of the history. Why is this becoming kind of a big deal in HPC? Then sort of transitioned into more of a sort of like, okay, let's get a little more tactical. And what does this mean in the context of what you do, what kind of problems you're trying to solve, either directly as a user, a system architect, an IT administrator, things of that nature. And then at the end, just sort of, from a lot of the work that we've done, I'll just sort of give you what I guess I would call like a cheat sheet. Here are just things to know that no one may put on a 1 or 2 slide postcard, but if you just do these things, you'll cover the first 80% of kind of what you need to know. A bit about me. I was going to skip this, but I was told, no, please tell us a little bit about yourself. So my real job is I'm a humble employee of my lovely wife and 2 little kids. If this talk gets disrupted, it's because the 3-year-old got away from mom and comes barreling in and decides to, God knows, do what. So they're my real job. My work job, my day job though, is I'm a principal program manager in Microsoft Azure on the high performance computing team for about the last 4 years. I am Azure's lead for the H series virtual machine. So that's one of the several core groups of infrastructure as a service products that you can get in Azure. H series is oversimplified. Think of it as CPU-based high performance computing. That's what it looks like. If you could physically see them in our data center, I know people who have never been in a cloud data center often wonder sort of what strange abstracted setups do we have. You would look at what we have and you go, oh, that's a HPC cluster. And that's what I lead inside of Microsoft. Before that, I spent about a year as a director of HPC solutions at Cycle Computing, which was then acquired by Microsoft. And before that, I spent the better part of a decade helping to run the private sector program, providing HPC cluster services at the National Center for Supercomputing Applications at the University of Illinois, either on infrastructure that was sort of custom tailored to the needs of our commercial industry partners, helping them utilize big sort of national science foundation scale assets like the Blue Water system that's amazingly still in operation. We're providing different sorts of scientific consulting services. So this was I figured I should just put this disclaimer up there because I've been on the other side. I've been a user at a place like NCSA, and I've heard a lot of people who are from a vendor give a talk. So what this is not some sort of marketing ploy. I'm not from the marketing team. I'm from core engineering. I would do lousy probably at marketing or sales. Certainly not either an explicit advertisement for AMD or against sort of organizations that compete against AMD or all alternatives to AMD, nor for that matter is this intended to be the most comprehensive possible discussion possible on this topic, because number one, that'd go for hours and hours and hours and hours that we don't have. But two, to really focus it really comes down to the specifics of an individual user. I could, even if I gave perfect, completely comprehensive sort of guidance or information to one particular kind of user, again, whether they're, most customers won't be in Azure. This is as much intended for people who aren't ever going to be an Azure customer or aren't right now. We're just trying to hit sort of the meat of what you should know about AMD EPYC, and so that it empowers you to take the next step, whether the next step is you feeling more informed about how you might invest in AMD EPYC, if that's something you're considering, whether you should get AMD EPYC, if that's the right tool for the job, because the premise of how we think about this, and I would encourage most people to think about all HPC infrastructure things, is it's a tool, it's a means to an end. The applications or the science or the engineering your users are doing is what really matters at the end of the day. What I really want to do though here in this discussion is just sort of treat this like every other EasyBuild talk, which is this is just a contribution to the broader HPC community from a group that's spent a lot of time working on and thinking about and skinning their knee and fine-tuning the topic that we're about to talk about. That's really it. And if that's a benefit to you in whatever situation you've got, fantastic. Like I said, we really want to be digestible and pragmatic, and something that's very core for me or for Azure. I generally find for most people who I talk to who want to have conversations about these kinds of things is they're looking for data-driven recommendations. Well, there will be a lot of data in this slide to back up sort of why we recommend something, so that this doesn't feel abstract or theoretical. And then, of course, as with any one of these talks, which is, feel free to, I don't see, I guess, the Slack channel. I think the EasyBuild organizers do, but ask any questions that you'd like, and I'll do my best to give not just answers, but data-driven answers to the extent that I can. And like I said, even if we don't have time, or if I don't have content prepared that speaks to the thing that gets raised, I told the EasyBuild organizers that or someone from my team would be happy to come back and give a follow-up talk if there's that kind of interest. So just why are we even talking about this? What's all the fuss about EPYC? Well, the big deal is that there is finally a credible alternative CPU for the data center after nearly a decade of one provider being sort of the solution that kind of everyone more or less had to use. And it's cool, you're actually starting to see a proliferation of more different hardware types than just AMD EPYC with ARM CPUs, things like that. I won't talk too much about ARM today, not because I'm avoiding it, but just so we can actually get through EPYC content in the space we have to talk about it. But that in and of itself is a really, really big deal. There's a credible alternative, especially one that has leadership attributes from a technology standpoint, or from a software compatibility standpoint, or from a what does it mean to my organization from a cost standpoint, that are better than what I or you have often been able to get for the last decade or so. That's a really, really big deal. If nothing else, it's great to have choice. And these are all things, of course, that we in the HPC world like to see. We like to see that heterogeneity, we like to see that competition, choices, different ways to think about new tools, solving the different kinds of problems that we have to help computational scientists get through. So the what is that? Quick history of AMD EPYC. So EPYC is only a fairly recent brand. It's been around for coming up about 4 years now, and probably like a lot of you out there, you remember the Opteron days in the 2000s. That really sort of technically it ended kind of in around 2012 or so with the pile driver system on a chip and the Abu Dhabi core architecture. But realistically, Bulldozer, what a year prior was their last sort of major stand in the data center. So you're looking at about a 6-year gap when with AMD not really having anything net new in the data center. And so obviously in the technology space, that's nearly an eternity. So AMD providing a new option into the market. They obviously, this is not like an iterative design on top of what they were doing 6 years ago. They came up with something called the Zen line of core architectures, the previous sort of 5 years or so, because that's how long it takes to design and build these things. And from there, they've been iterating, and it started with a chip, a core architecture called Zen2 in 2017. In a processor whose code name was Naples. It's all under the EPYC brand name. And that was a really credible sort of first stab. When they came out with Naples, that was, to put that in context, when Intel had released Skylake, and at the time, sort of the high volume parts around Skylake that they could make, that Intel could manufacture at good yields and the levels that were cost effective for a lot of customers were sort of in the range of about 16 to 20 cores. You could go higher. You could go to 24 cores, 26, 28, but the yields on those were substantially worse, and the cost went up quite a bit. So it wasn't usually a terrific performance per dollar play for a lot of customers. So for AMD to come in and out of the gate in 2017 with the release, it was more or less co-timed with when Skylake came out, and go, okay, we've got roughly 50% higher core count, and we've got 33% more memory bandwidth. We've got the same I/O capabilities. That was a really credible re-entry into this space. It didn't make them sort of a hands-down winner. The Zen1 core was certainly lagged behind an Intel Xeon core, just from a raw core throughput standpoint. It didn't have the world's highest IPC, didn't have particularly high frequencies. But for a lot of us in the HPC community, we took note, and some of us even invested because a lot of our applications really, really like memory bandwidth. That will scale pretty close in line with memory bandwidth. And the second one is the performance per dollar was really attractive. Where things really took a sort of a step function change was around 2019 or so, when Rome debuted. And Rome was a big deal because you have to remember that for going back to, let's call it, let's call it the Sandy Bridge architecture. Most releases from Intel, like, to Intel's credit, significant credit. Intel has always been a participant in the space. They've always been introducing new products in one form or another, and those among us can take issue in terms of whether the products came when we wanted them to, whether they had all the right features or uplifts that we wanted. But the fact is, Intel has always been a strong presence in this space. They've been there. If you need to do HPC, Intel's been an option you've been able to go to. And there's a lot of value in that. But part of being able to execute that meant that a lot of their releases were more iterative. There weren't, titanic, if you had Haswell processors, there wasn't necessarily a gigantic leap as opposed to going to, say, Broadwell. You go from DDR4 2133 megatransfer memory to 2400. You go, okay, it's about 10% better memory bandwidth, that kind of thing. Rome was a different story. Rome was, oh my goodness, all of a sudden, core counts as much as double, up to 128 cores in a 2-socket server, a standard 2-socket server. Memory bandwidth jumped again all the way to about 340, 350 gigabytes per second, which, to put in context at the time, you're still talking sort of Skylake, Cascade Lake at around 200-ish gigabytes per second in terms of real world soakable. So still a really big difference in memory bandwidth in that regard. And PCIe 4.0, so it was sort of it was the first x86 platform. Power got there first, all up, but it was the first x86 platform that supported PCIe 4.0. So this was a great platform to drop in things like 200 gigabit HDR InfiniBand, which is one thing we did in Azure, or PCI Gen 4 accelerators, which a lot of sort of the new GPU systems you see coming out now are based off pairing Rome with like A100 accelerators, things like that. And then a few months ago, AMD did something really interesting. They released something called Milan. Milan being a follow-on to Rome that features, we'll get into sort of similarities and differences, but it's sort of their latest release. And while it doesn't change a lot of sort of things going from Rome to Milan that you saw going from Naples to Rome, it does introduce some really materially helpful things for those of us in the HPC community. So it's a very interesting system architecture in that regard as well. Not just interesting, value adding, I would say as well. So what's really different about AMD? Like, how did AMD get to 64 cores, really quickly when sort of what we, for a lot of folks out there, in our role in Azure, a lot of the time when I talk with customers and I'm only referencing this as a sort of set of data points in terms of where are a lot of HPC customers still. We say, okay, what is your primary sort of compute infrastructure that you're coming off of that you have right now? There's a lot of folks out there who are still using, Broadwell or Haswell infrastructure in production, which great, that's awesome. There's nothing wrong with that. Even Skylake infrastructure, as well, more modern. You're still talking about core counts in the range of, let's call it, 10, 12, 14, 18, 20 cores on a die. Part of what enabled AMD to just sort of go to these much higher levels is they were sort of the first major data center company to embrace this notion of chiplets, which is essentially saying my processor isn't going to be just one big kind of monolithic block of cores. And I'm very much oversimplifying it, but this picture does a good job sort of depicting what I mean here, where you can clearly see there are on this processor, this is a die shot. If you were to pop up the heat spreader of a Rome processor, you'd really see 4 different quadrants of processor cores. That's what those black squares are. Each quadrant is connected through that central IO die, and then each one of those quadrants gets its own 2 channels of memory attached to it. And so from a marketing on the box standpoint, what it could describe as a 64 core 8-channel architecture. Oversimplified, yes, that's true. It's true that there's 64 cores in the processor. It's true that there are 8 channels of memory going into the socket. But in many ways, this is more. It's more like saying there's it's 4 16-core quadrants, each of which gets 2 channels of memory hung off of it. And that really matters because you really need to start to think of all these things as these modern processors and as almost like clusters on a chip. And AMD is probably the most well-known and among the earliest to embrace chiplet design. But realistically, most chip manufacturers are going to have to go into this direction in order to continue driving up aggregate performance per socket, which you have to always remember, that's the actual consumable unit. That's really what you buy. You don't buy, cores, you buy a socket or you buy servers or n number of servers. This increasing hardware complexity, though, does have some really, really substantial benefits. And it makes sense why AMD went in this direction. The first is that it can have a really material difference on fab yield percentage. Fundamentally, when the larger you make a physical monolithic die of cores, just as it physically gets bigger on the SoC, the higher the probability that an imperfection in the fabrication process, which will always occur at some level, is going to occur somewhere in your monolithic die and cause you to have to throw away the whole chip. And so by making lots and lots of little dies and connecting them with smaller interconnects on the package, you can dramatically increase the yields from the fab and lower your costs, because you're making lots and lots of lower cost, higher yield parts, and then this is connecting it together, rather than trying to make a larger and larger physical die each time. That part's really challenging, especially when, as you've seen, or as many of you have seen anyway, we're not making the same rapid advancements from one chip fab node technology to the next nearly as quickly as we did 10, 15, 20 years ago. So innovations in packaging and fabrication are in many ways now sort of the greatest drivers of the ability of any given vendor to drive up the core performance of their products. I will tell you, my personal guidance is, I would say it's not, don't listen to what a vendor says to you, in the roadmap discussions, but to a certain degree, like anyone can make a roadmap slide that says, oh, we're going to do this, we're going to, this is what our product will do. It's not a bad idea to probe people on, well, how are you going to make it? What's your confidence that you can make it? What are the risks and dependencies from a fabrication and packaging standpoint? Because that's a lot of that determines who ends up being able to bring what to the market and when, and at what cost and at what power consumption level. And don't forget about the power piece as well, too, because for a lot of us, power or indirect costs are a really big percentage of the total cost to run a HPC environment. So power efficiency still really, really matters. We have certain, I run into a not insignificant number of customers in Azure who in their on-prem environment, they have, their biggest gating factor is they have no more power or physical colo space that they can use. So in order to make a upgrade in place, they need to take out a server, put in a server, and they have to stay at ISO power. They can't consume more power. They have to get as much performance increase as they can without actually changing their power or physical space footprint. Lots of us in HPC are fortunate we don't have that situation, but there's a kind of where you are, there's a pretty good chance somewhere along the lines, you definitely care about power. So Milan versus Rome. So what's actually the difference between these two? How much do you care? They look physically from an overhead view standpoint fairly similar to one another, and that's true. They do at a certain level. You will see AMD often calls it sort of an 8+1 die technology or layout, where you've got the IO and memory die in the middle, and then you've got these quadrants of chiplets in the corners. Rome and Milan have a number of things in common that you should fully expect and should be surprised at. They support the same core counts, same max TDPs. They both support PCI Gen 4.0. They both support the 3200 mega transfer memory, which in data center memory is the highest memory standard you can go to. And they have the same level of inter-socket connectivity between the two in a two-socket configuration. I should have actually mentioned you can also get both in a single socket configuration as well, if that's what makes sense for you. There are a couple of really key differences, though. The first is, if you look at Rome, what you really see up here is that you've got 4 cores, each of which shares a slice of 16 megabytes of L3 cache. And in Milan, they've collapsed 2 adjacent chiplets such that any one of these 8 cores now can get access to all 32 megabytes of L3 cache. So aggregate cache per chiplet, per quadrant, per socket, per server isn't any different between Rome and Milan. But the directly addressable cache per core, the ceiling on that has gone up by a factor of 2. The next relevant thing is that there's much higher instructions per clock from Zen 3 to Zen 2, close to about a 20% uplift So this is sort of it's a brand new core architecture. Zen 2 was essentially a big refinement of Zen 1. Zen 3 is a brand new core architecture itself. You will generally see higher frequencies on the Milan side of things, simply because the 7 nanometer manufacturing process at TSMC, is where AMD makes its chips, has gotten more refined. AMD has gotten more refined at it. They're just kind of better as these kinds of companies get more swings. That analogy may not go over well in Europe. As they get more attempts, they get better at knowing how to tweak frequencies without materially affecting power. And then the last thing is that there are memory latencies improve on Milan. In Rome, the data fabric that connects the cores to the memory runs at a max speed of 1,466 megatransfers. And the memory can run up to 32. And what you would notice about that is 3,200. 3,200 is not 2 times 1466. That would be 2933. So if you want to have your memory clock and your data fabric clock be in sync to get the best memory latencies, on Rome, you'd actually want to run it at 2,933 megahertz memory, even though it supports up to 3,200. On Milan can run at 3,200 with a data fabric clock of a full 1,600 megatransfers per second, which puts it in sync with the top end memory speed. And as a result, memory latencies get better as well. So, okay, talked about what is EPYC, what's the deal with it, what kind of inroads is it making in HPC? Well, HPC is probably the space, or among the spaces, where EPYC is making the fastest and most substantial inroads, just because we as a community tend to index so much on performance and performance per dollar. And if there's a material shift in what can be gotten in the market to hit those sort of key metrics, then we as a community tend to move toward those things more swiftly than the broader data center, IT market does. And that is well reflected in the last June 2021 top 500, where if you look at new systems by CPU vendor, AMD actually was the leading new entry. Intel's still right there. Like I said, Intel's super strong. We do a lot of work with Intel ourselves. Again, this is not an advertisement for AMD. I'm talking about our experiences using AMD for a lot of HPC and AI things inside of Azure, but we also do a lot on the Intel front as well, and for good reason, and so do our customers. But as the data clearly shows, AMD is clearly getting noticed, and not just getting noticed, but people are investing. They're betting their HPC futures, or at least the next visible system horizon on that. And you see that reflected especially in a lot of the leadership class systems. The new, I think, number 5 system, Perlmutter at NERSC, uses AMD CPUs, pairs with A100 GPUs from NVIDIA. Lumion, a really cool system coming online pretty soon at just over half of an exaflop peak, is based on AMD CPUs and AMD GPUs. Frontier, which probably, I'm not saying this from insider knowledge, but sort of from all public evidence, it appears to be sort of first in line to be the first sort of 1 exaflop HPL FP64 system is an AMD CPU plus AMD GPU system, and then so is a follow-on system that the U.S. Department of Energy is deploying called El Capitan, that features sort of successive generations of technology from what you find in Frontier. That'll come online, I think, about a year later, and is intended to eclipse 2 exaflops. So you're definitely seeing a return to the high end of the HPC space, which, a couple things. One is that tells you the leading supercomputing sites are commonly, not exclusively by any means, like this is I'm showing you a slide of sites that have made the decision to use AMD as a core part of their system design, but there are plenty of other systems and sites that have decided to go in a different direction, and that's fine. This is by no means a statement of AMD is the only way to get there, but but certainly a not inconsequential percentage of the market is recognizing that AMD has some real game in this space. But the other thing to bear in mind is even if you work in an organization where you as a user, you're not going to be deploying, exascale class applications or deploying exascale class systems. It's important to remember that the sites that deploy these really big systems, they are under tremendous pressure to wring every drop of performance per dollar cost efficiency out of their grant dollars. Just as you might be, whether you're in a research setting or you're in a commercial setting, everyone's got a budget to deal with. Everyone's got constraints. You're trying to make your funding go as far as possible. And so part of the other lesson, I think it's good or instructive to take from sort of AMD, the awards that AMD technology has gotten in this space, is that a lot of people are saying that this is a very good value investment as well. Again, just to, under the heading of, this isn't, I'm not showing this, as an Azure advertisement, but just so to stress the point of I'm not just a guy commenting from the sidelines, about what others are doing and saying, oh, you should go do the same thing. We ourselves have made a lot of these decisions ourselves. We have skin in the game. We've made investments in our CPU and GPU, HPC and AI portfolio that have a lot of AMD technology underpinning it in support of our customers' workloads. We've done actually all 3 generations of the EPYC CPU line for CPU-based HPC, starting with our on the HB series side of virtual machines, starting with Naples that we went to essentially production, what we call general availability in 2019 with 100 gigabit EDR InfiniBand, incrementing that a year later to Rome with 200 gigabit InfiniBand. And then we were fortunate enough to be ready right when Milan had its sort of big unveiling. We were able to release HBv3 with Milan and 200 gigabit InfiniBand back in March of this year. So we've been doing a lot with EPYC on the CPU-based HPC front. And then we've also been using AMD as a platform for our most powerful accelerator-based systems as well. So we recently released a virtual machine product called the ND series that's targeted at deep learning, but honestly, it looks an awful lot like what a lot of sort of leading GPU compute houses would use as well. It features Rome processors and 8 A100 GPUs from NVIDIA with NVLink, and it has a lot of network bandwidth. We've got 8 200 gigabit links coming out of it. And that part I would stress too, because one thing I realized is even though we and folks on our team live in this day to day, a lot of folks still, when we say, well, we're doing HPC and, in a cloud provider, they assume what we really mean is we're just, you're doing web servers and you're just calling it HPC. It's like, no, we actually really build HPC and AI supercomputers. And we have we have the latest network technology. We do a lot with InfiniBand. And I'm not showing this off as a advertisement for Azure, but just only insofar so that people can see that I'm speaking as someone who, I'm speaking, of course, always on behalf of a larger organization. But when we talk about these processor technologies, and I've thus far mostly talked about all this stuff in the context at a sort of an individual server level, we think in terms of the products and infrastructure and services we design at the cluster and system level, much in the same way that you all in the HPC space do. So just bear in mind, I'm keenly aware a lot of you will be thinking about, well, how does EPYC fit into a scenario where I'm thinking about my technical or buying decisions or software support decisions at a cluster level? We totally get that, and definitely going to try and cover those sorts of scenarios today. And yes, sorry, by the way, this is what these sort of combinations of sort of very high performance focused system design coupled with what people would readily call HPC class interconnects and InfiniBand enable us to go do. We can run some really big applications on Azure. I'm not going to get into the detail other than to say, if you were to look across the bottom, you'd see, number one, we're running big applications both with Intel HC is the name of our Intel-based CPU line. It was actually the first, I think that was the first platform we used to run a 20,000 core MPI job a couple years ago, right on ISC 19, which was a lot of fun with CP2K. But the real takeaway here is, these are all AMD based VM offerings. These are all Rome here so far. But the whole point is we're running a diversity of applications at scale, much as many of you in the HPC space are tasked with doing in terms of supporting a diversity of users with demanding applications. So, okay, giving you the background on EPYC, I've done hopefully a passable job at explaining why I have any right whatsoever to give you any guidance or recommendations on this topic at all from our time working with EPYC and the AMD team in Azure. Okay, let's start talking about what does this mean to you? Of course, this is, and it depends. As with anything HPC, the key thing to start with is just what are the most important problems you're trying to solve for, and how do you explicitly stack rank them, right? When push comes to shove, what are the really important things that you have to solve for? And I'm not going to walk through each of these. I think these are probably all sort of topics that many of us think about constantly. Some of us have to, these are almost like the primary functions of our roles. But with any HPC infrastructure decision, the best recommendation I give you, even though I happen to be talking about EPYC processors today, don't approach any of these technical design decisions from a fan of one company or another. These are all tools to get done the work you're trying to get done, and really start from that. Don't confuse the means, the infrastructure, as fun as it is, from the end goal here, which is usually some version of we need insight, we need science, we need engineering, we need, we need to save time, we need to cut costs, something like that. Like those are probably going to be the most important things that your organization is tasking you or your leadership with solving for. So starting from that, that's always the first order thing I'd recommend that anyone think about. And if EPYC fits really well into that, and there's a good chance that it'll be a compelling option for you in that regard, great. Just make sure you get the order of operations right. One thing I can say that I'm guessing applies to at least some of you watching is that a frequent answer we hear from, I say Azure HPC customers, but when I was at NCSA working with either researchers or working with commercial partners, I want the best performance or cost performance for my most important workloads with as minimal sort of hassle in terms of having to know how to use the new hardware as possible. Some version of that kind of statement. Doesn't mean that's exactly fits your profile, but good chance it applies to at least some of you in the audience. So, okay, you're going down this path, you're going to get some CPU-based HPC. And by the way, I should clarify, most of my guidance today will be around the context of using EPYC for CPU-based HPC as opposed to EPYC as a platform to run accelerators. That's an additional talk we would be happy to give, but just trying to cram too much into one conversation. Okay, so you've decided you're going to go get some HPC, or you're thinking about it, or you've already got it. What should you expect? Well, the first is EPYC performance as a general matter can be really, really good for CPU-based HPC, especially if you're in the camp of folks who are only getting new infrastructure into your organization every, let's call it 3 or 5 years. If you're coming from a lot of like Skylake, or even we have a lot of customers who are still coming off of Haswell and Broadwell. It's very, very common for people to buy and run infrastructure for 5 years at least at a time. So a lot of the time when they, realistically, anytime you wait 5 years between going from one HPC technology or another, you're going to see a big jump, and Rome and Milan certainly fit that bill. How good depends on what your workload really scales with. You'll hear this as a recurring theme here, which is it really comes down to what you're trying to do and what your application is most sensitive to and what you're most sensitive to. In Azure, where we see a big diversity of workloads, and I know that maps to a lot of sort of research institutions. We've got researchers coming from all over a campus with different sorts of requirements, different sorts of scientific and engineering domains. We have some applications that scale almost linearly with memory bandwidth, some that are extremely sensitive to L3 cache. They might be super memory latency effective. Some are very compute dense. We have applications where the code hasn't been updated in an extremely long time. And this actually happens a lot in the commercial space. There are a lot of commercial HPC applications that haven't been updated for so long a time that the instructions, the hardware instructions they were originally coded for, have been deprecated from modern CPUs. And so the way that those instructions get processed is in software, which means they scale very closely with frequency. That happens as well. So understanding sort of how good EPYC is for you really comes down to what kind of a problem are you trying to solve here? What does the workload need? What are you sensitive to? The main thing I urge everyone to realize and center your head at is performance or cost per job, per workload. That is actually the bottom line thing that matters. Don't think about scaling by cores. You don't buy cores. Sometimes I have people come in and they'll say, well, I ran, say, 3 120 core EPYC VMs in Azure, and I ran it to get 360 cores. And then I ran, the same number of cores on the Intel side. And they go, but the Intel one performs just as well, it performs better. And it's like, yeah, because you threw many more servers at the problem. The way application performance scales is by scalable, or you scale it from a performance standpoint at the server level, and then for MPI workloads at the n number of nodes level, scalable RDMA endpoints or network connected endpoints. And more also to the point, that's not even what you're buying. You buy or you rent servers, not individual cores. And don't get too caught up in this era of exploding core counts if you're using all the cores. I think a lot of people go, oh, if someone tells me I shouldn't use all the cores because I want to maximize, say, memory bandwidth per core or memory per core or cache per core, I'm wasting the server. No, you're not. If you run on a GPU, if you've ever played a video game in your life, do you have any awareness, how many CUDA cores you're using in your system? Like, do you stress out if your application didn't use all the RAM in the system or the cache? How many of you are even tracking some of those things? The key thing is, what's the configuration of a given server that gives me the best performance or performance per dollar? And where that comes into play, if you haven't bought something yet, is go test these things out on resources you can get your hands on, either at a research institution's supercomputing lab. Obviously, cloud providers is a general matter. It's not an Azure statement. You can go test out AMD processors from Amazon or Oracle or Google or Azure. See, I went out of my way to, or even IBM. I went out of my way to make, say, Azure last there. Go test that out. Find the right fit for what you're doing. Also, don't just assume that clock frequency equals performance. Don't just say, what's the higher gigahertz? Higher is better. I'm going to go do that. Frequency can be a contributor to performance, but it does not equal performance, certainly not in any kind of absolute terms. There are plenty of cases where a core architecture running at a substantially lower clock frequency, I'll show you examples in a second, even with fewer cores, will vastly outperform a alternative core that has much higher clock frequency, right? So, and more cores to throw at the problem. So don't just, I call it the more gigahertz factor. Understand what your applications are trying to do. And I understand that's a difficult balance to work. A lot of scientists or engineers don't know these things. But as a system architect, try to lean in and understand what your customers' workloads are really scaling with, so that you're providing the right system configuration, either in the infrastructure you're buying or in sort of scripts or tunings you're giving your users to use in order to get the most out of that infrastructure. One thing I will tell you, and I know to a certain degree, usually when I say this, I usually get 2 reactions from people. One is people nod their heads because they know, and the other reaction is people cringe a little bit because they're thinking about, oh man, I'm going to have to tell my users how to do this. Is we're definitely entering the era where the hardware topologies are getting sufficiently complex, and chipletized that you really don't want to just say, throw my processes at the server or the VM, a VM is a server, and just sort of count on the application or the OS to do the best possible process layout and to have a perfect understanding of how system resources are being balanced. You really want to be aware of how to evenly distribute processes and explicitly lay out your software over that hardware as a result. In the case of Rome and Milan, the simplest, the best advice I can give you is go back to that sort of chiplet thing I mentioned before, where in Rome, an L3 boundary is every 4 cores. So that's, in Milan, it's every 8 cores. So think about incrementing up your process count, generally speaking, by incrementally adding cores per NUMA domain, where in this case I'm defining, or cores per L3 cache boundary. So in a Rome server, like a dual 64-core socket server, you actually got 16 4-core L3 boundaries per physical socket, 32 per node. The best way to scale up, if you want to provide max performance to all the core, not just max, but also load balanced, is to increment up by the number of cores that you're utilizing per what AMD calls CCX or 4-core chiplet. So that results in ideal core counts of things like 32, 64, and 128. Don't just assume that, say, 36 is better than 32 from a submitting core count standpoint, because yeah, you're throwing more flops at the problem, but now some of the cores are contending for things like access to DRAM bandwidth or access to cache or access to data fabric bandwidth in a way that other cores aren't. That imbalance can cause all sorts of performance problems. So the simplest thing under the heading of, like, if I remember nothing else, just evenly allocate processes by what AMD would call the CCX or the CCD, by your physical L3 boundary, which again in Rome is every 4 cores, and in Milan it's every 8 cores. So this is something to know too. So you'll hear people say things like, well, or you might ask, well, of course AMD, seems faster, but the cores are slower, than Intel still, because if I divide, the performance I get per socket on the AMD side by the number of cores and do so then on the Intel side, then I still get a higher per core performance. No, not necessarily. You have to remember per core performance is never fixed, especially in HPC. It largely depends on how cores are subdividing global shared assets like DRAM bandwidth, level L3 cache capacity and bandwidth, data fabric bandwidth, which is literally the data fabric connecting cores and memory within a socket and then socket to socket, or to things like PCIe, power and thermal headroom allocations per core change as you increase or decrease the loading on cores. These things really matter. So here's an example of a very memory bandwidth sensitive code. I'm using ANSYS Fluent. ANSYS Fluent is going to scale very closely in line with memory bandwidth. And what you'll see here is, this is me taking, or this is not me, it was a gentleman on our team who took an HBv2 server, which is our VMs for AMD Rome. So think of it, under the hood, it's dual socket AMD Rome, 64 cores. And you're in the same problem, and he scaled it. We have to hold back a couple of cores for the hypervisor, such that the key sort of sensible scaling points in our case are 30, 60, 90, and 120 cores instead of 32, 64, 96, 128. And what you'll see here is, if you just looked at these bars, you'd go, well, wait, in this case, the 30 core job is providing still the majority of the performance of the 120 core job. Those cores must be stronger. Or, what magic happened? Nothing happened. It's the same cores in the exact same server. Each core just got a larger slice of these key global shared assets. And you'll see that there's a curve and a flattening out to this. And not all applications will look like this. I picked an application that is almost extreme in the degree to which it occurs, a very memory bandwidth sensitive application, but it nevertheless is sort of good at illustrating the point. Even if I go to something that's more compute bound like LinPack, you'll still see something of a similar phenomenon. So here what you're looking at is LinPack, very compute bound, not nearly as memory performance bound. And what you'll see is, as I'm taking, this is me taking or us taking now an HBv3 server. Now, as we load up core counts, again, just loading one core per CCD, per chiplet, you'll see that the stated expectation in terms of delivered HPL efficiency per AMD's guidance actually slightly decreases as you increment upward. So by the time we get from using one core per CCD to 6 cores per CCD, which in a dual socket, 64 core per socket Milan server would be going from 16 cores all the way to 96 cores, the expectation around delivered HPL efficiency actually declines from about 90% to 85%. And why did that happen? And the reason is because you start to overtax the data fabric of the processor. And so it's not as pronounced as we saw on the memory bandwidth bound application like Fluent, a CFD application that's just doing huge amounts of information passing. But it nevertheless, even for a compute bound application, you can see this principle of per core performance is never fixed. It really, really changes based on how you're loading a server and what kind of application you've got. So I've given you examples so far sort of within an AMD node. Here's an example of sort of I was alluding to before, which is, and this is part of what makes EPYC really good, which is EPYC as a platform, it packs in so much memory bandwidth, cache, data fabric performance that for many applications, even at ISO core count, you're gonna see it outperform Xeon, even if you reduce it down to the same core count. So I'll be really clear. I'm taking this from a blog someone else on our team published. This is not a shot at my colleagues in AWS. I have friends in the AWS team. This is a plot from their public data, but we could have run this with our HC series that also uses Skylake processors for HPC. And the plot line, the orange line, or I guess that was kind of goldish, would look very similar. The blue line here, so this is the AWS C5N 18X large instance. It's a 36 physical core Skylake box. Again, I want to stress, the line would look very, very similar if we were using our HC series. I just pulled this because this information was already public and had the data at the ready. And what you see here is I'm showing HBv2 Rome run in 2 different ways on the same problem with OpenFOAM. And what you see is, yes, the OpenFOAM with 60 cores, so more cores than what's going on here on the Skylake side, performs better. In many ways, that intuitively wouldn't surprise people. But what may surprise people is that even if I go down to 30 cores, so I'm now using only 5/6 as many cores as you see on the Skylake side, we're still running at basically 2x the performance of what's happening on the Skylake side of things. And by the way, these Skylake cores are running at 3.5 gigahertz. These Rome cores are running at 3.1 gigahertz. So there's basically a 80 to 85%, only 85% as many cores and clock frequency on the Rome side of things, yet the performance is double. That's how impactful this huge amount of global shared assets can be in terms of even if you want to run comparisons at ISO core counts, it can be in terms of altering sort of the performance comparisons on a per core basis. Here's another one that really matters. Here are cases where I'm just going to show you 2 different examples. Know the scale of what you're going to go target here, or at least the scale of your most important workloads. Because how relevant is EPYC to you, or how relevant is either in the context of, say, EPYC versus Xeon, and again, not to shortchange, Ampere or something like that. I just know that for most folks looking at CPU HPC, they're still looking at on the x86 side. EPYC versus Xeon, and then even EPYC within Rome. So let's take a look at CP2K. if you were running a lot of CP2K jobs and you said, my users run a ton of CP2K jobs, they generally run them at relatively small scale, about 4 nodes at a time. What you'd see is, wow, there's a huge difference between a high performance Skylake offering. And this is we have a very, very good Skylake processor. We have the dual 24 core high parts, the Xeon Platinum 8168 parts. This is basically as good a Xeon part as you get from the Skylake generation. It's better than a lot of the Cascade Lake parts. You see about a 2x performance delta there. But then as you scale the problem out, once you get to, let's say, 128 nodes, no longer do you have a 2x delta, which is 2x is kind of hard to ignore for a lot of folks. Now when you get to 128 nodes, the difference, I realize that you probably having to squint a bit to see it here, the difference between Rome and Skylake is kind of down to more like 20%. How you think, how big a difference is 20% versus 2x? That can be a pretty big difference. At 20%, that's nice. Don't get me wrong. 20% is awesome, but for a lot of folks, they may say that's not enough for me to not just sort of keep buying the Xeon stuff I know or I'm comfortable with, and that's okay. We get that as well. But again, it illustrates the point of there's a lot of sort of what makes the most sense for you will depend on what's the level of scale. Now I'm going to show you the reverse scenario, which is, and this is something that's really cool we've observed, which is that what makes Milan, you remember earlier in the talk, I mentioned that Milan is really good for HPC in a number of ways. Milan's superpower, if I were to distill it, is that the larger you run an application at scale, the greater the benefits it has over Rome and any other architecture. So remember before when I showed you that slide about us running a lot of applications at really large scale with Rome, a lot of people buying Rome for big HPC systems. Rome can do great for scale. Rome, the biggest jobs we've run in Azure on the CPU side to date have actually been with Rome. We haven't gotten around to doing the biggest scaling stuff with Milan yet, but we run 80,000 core Wharf jobs, 86,000 core NAND jobs. Rome is awesome for scale. This is not a comment about Rome can't scale. Rome scales terrifically. Milan scales kind of amazingly. And this is what I mean. So here's the same ANSYS Fluent problem. And what you'll see is if you're running a 1-node version of this memory bandwidth bound problem, it's about a 15% difference between the two. By the time you get to 64 nodes, you've got a nearly 90% difference in performance. The larger caches and the smarts of that cache are materially different on the Milan side of things. Again, it just illustrates, this is sort of the inverse demonstration of what I showed you over here, where there was a big gap at small scale that narrowed at larger scale in some ways. This is the reverse. Relatively narrow gap at small scale can get pretty darn big at larger scale. Know the level of scale that you want to run your application at. AVX 512 support. How big a deal is it? The most pragmatic, and I say this as someone, bear in mind, I should have clarified at the beginning. For as much as we've done in Azure, with AMD and EPYC, literally every system I ever built when I was at NCSA, and still systems we design and productize in Azure are Intel-based. I've deployed more Intel-based stuff for a very, very long time. So again, this is coming from someone who's got a lot of experience deploying and supporting users on both kinds of platforms. How big is a deal is it that AVX 512 support is not in AMD Rome? My pragmatic answer to you is there's a high likelihood it's not a big deal or it's no deal. Pragmatically speaking, just brass tacks, there's not a ton of AVX 512 applications as is. It's just most applications haven't been optimized for that. And there are even fewer that are heavily optimized for it. More to the point, EPYC does have AVX2 support. And pretty much, what's the application that, I haven't encountered an application yet that has AVX 512 support, but no AVX2 binary to go with it. And the reason why that matters, you go, okay, well, but AVX2, 512 is twice as fast as AVX2 is. In theory, that's not quite true. Intel's got to take a hit on clock frequency. They fixed a lot of that actually in Ice Lake. They've done very well in terms of fixing that with Ice Lake. But you have to remember, okay, well, what does AVX 512 actually gets you? So what that actually does is it improves the actual delivered flops for a given application, all right? But let's think about how you actually calculate flops per server. So here's scenario one. You've got two standard, two CPUs in a server. I'm giving Intel the benefit of the doubt, but the top end Cascade Lake, 8280 parts, 32 ops per cycle, which is what literally AVX 512 means. And then a sustained clock frequency of around 1.9 gigahertz in that sort of SIMD bound scenario. That's probably what you get from a top end Cascade Lake part. You'd see around 3.4 teraflops. Do the same thing on the AMD side of thing, and then you go, okay, I only support 16 ops per cycle, but now I've got 64 cores per node. So yeah, I've got half the multiplier effect over here, but I've got greater than 2x the multiplier effect over here. And the result is I get more aggregate flops actually on the AMD side. And oh, by the way, I didn't have to recode, just kind of use more cores. Now, this isn't true. I want to be really clear. This isn't true for any and all applications. There are exception scenarios. Like if you have an AVX 512 application that is licensed, say, per core, and the software costs dominate, and the problem isn't communications bound. In other words, you're not going to somehow scale it to some significant level. So in other words, think of a scenario where you as an organization, you license some application. That application costs way more to license than the cost of the server you're going to run it on, and you only say license 16 cores of it. In that scenario, you're probably going to get more performance out of the Intel, the Xeon side of things, because you're rationally incentivized not to just use more cores on the AMD side because it would blow up your licensing costs. So you don't do that. So you go, I basically get the most performance out of the number of cores that my software license allows me to use, essentially from a budgetary standpoint. Perfectly fair. That happens plenty of times, right? So those sorts of scenarios like Xeon will do better in that kind of case. With that said, one big picture thing to have in mind is if you have an application that is so incredibly flops bound, you probably want a GPU anyway, just because GPUs are so much better at these kinds of current computational kernels than a CPU. And obviously there are exception scenarios because if you've got to buy one kind of infrastructure that can run a broad set of applications, yeah, maybe a CPU still makes sense for you. A lot of customers make that decision. But principally, if you're as an architect trying to support users and your organization, if you have to run a lot of workloads that are very, very compute bound, and you're going to buy something for the next N number of years, it's good to think about the EPYC versus Xeon question, but you should also think about, is a CPU even the best path for me here, and have a really clear data-driven view as yes or no in that regard. MKL support. MKL is wonderful. It's very, very, Intel does a great job with MKL. This is one of those that I'd say it's a summary statement is, it depends. In general, it runs just fine on EPYC. It's not that it won't run. The real issue is that Intel isn't going to provide support for it. They're not going to say, yeah, we've done the deep dive investigation into whether MKL running on top of a competitor's CPU adheres to IEEE numerical standards in the way that we've done for our own processors. They haven't done that. But pragmatically, if you throw like an MKL problem or an MKL-based application at a EPYC server, will it run? Yeah, it'll run just fine. How big a deal will it be? Kind of depends on how much you care about the performance impact. Over on the right, I've sort of given you a view of sort of what pragmatically the impact will be. If you're running in the now disabled debug mode, which is a tuning you could do in MKL prior to version 2020, where you could disable a check that MKL would do for an Intel specific processor and would provide full acceleration to a competitor like AMD's their processor, you'd see basically full acceleration. When it got disabled for multi-core DGEMs, you see a pretty big performance impact. The guidance I would give you, if you have access to source, is AMD has a very robust set of libraries. I dropped in a link here. Their Bliss library has gotten very good. Lots of widely used applications now have Bliss support. and AMD well supports it. So it's perfectly safe. Lots of applications already support it. And as you will see, Bliss running on, an EPYC 7742, which is very much like the processor we have in Azure, or you could go buy for yourself, or you may have already bought. It'll actually, from a peak compute standpoint, it'll actually do better than running debug mode of MKL on top of an AMD processor. And of course, like I said, there are scenarios where the guidance, the scenarios I just gave you, actually, you wouldn't feel comfortable doing that. Like, let's say you work at a company, you license some core application, you depend on running in supported scenarios from your key software licensed vendor, and now you don't want to muck with what they say their supported matrix of hardware and software is. It's a perfectly acceptable outcome to say, yeah, that's a scenario where it's like, even if there's less theoretical performance on the Xeon side in terms of, can I get the performance I need in a supported and compliant way from my, P0, my priority zero software vendor? Cool. Then I'm going to go do Xeon. That's the right rational decision for me. That's a perfectly acceptable outcome as well. Me saying you can use Bliss or MKL runs fine. That's not a statement of there's no scenario in which you wouldn't explicitly want to pick a Xeon-based platform because of its robust support within the MKL using community. All right, final sort of some BIOS settings, some cheat sheet things to know, things that are publicly available, but I don't think you commonly won't see them distilled to a single scorecard. BIOS settings to know if you get an EPYC server for HPC. The first is the L3 as NUMA setting. This essentially defines how the server will expose a NUMA boundary. If you set it to 1, then you will get a NUMA domain for every L3 slice, plain and simple. So in Rome, that'd be up to 16 NUMA domains. In Milan, that'd be up to 8 on a per socket basis. If you disable it, then the number of NUMA domains you will see within your server or virtual machine comes down to how you set this adjacent sister setting called nodes per socket, or NPS. NPS equals 1 while setting NUMA, L3 as NUMA equals disabled. That will expose an EPYC processor like you're used to seeing from a Xeon processor, which is one big monolithic NUMA into the operating system in 2 applications. Now, under the hood, as you've seen just from like the physical die shots, they're not like there's disparity in terms of any given core's access to, say, its local memory, its local cache versus remote memory and remote cache, right? But from a software compatibility standpoint, that's the thing that makes NUMA presentation as simple as possible. L3 is NUMA disabled, NPS equals 1. NPS equals 2 will make it look like you've got 2 NUMA domains per socket. So it increases NUMA complexity a bit, but not too much. You go from 1 NUMA domain per socket to 2. And that what it literally means is it's doing 2-way memory interleaving. And then NPS equals 4 is 4-way memory interleaving. We actually started on Rome. We did NPS and Azure. We did NPS for L3 as NUMA equals enabled. So you see the max amount of NUMA complexity there. And we did so because we were really early with Rome. And at the time, AMD hadn't yet collected a ton of data about comparing all of these different options pragmatically with different HPC workloads. Over time, as we and they collaborated on running more settings, what we found was it was actually okay to disable L3 as NUMA and to set NPS equals to 2. You're not really giving up any performance. Theoretically, you can give up some performance, and you can measure with something like Stream Triad a minor hit to things like memory bandwidth. There can be as much as about a 50 gigabyte per second drop in memory bandwidth per server if you did the simplest possible NUMA presentation versus the most complex and localized. But pragmatically, from a real world application standpoint, what we've discovered, and we ourselves live now on our HBv3 virtual machines, which are our Milan-based virtual machines, is L3 as NUMA equals disabled, NPS equals 2. And if I had to make one recommendation, like what's just, tell me what to do, I'd pick those 2. The next thing is something called determinism mode, which is a way of telling your every individual server, should I keep clock frequencies to some common denominator minimum across a cluster? Or should I let each individual server try to boost clock frequencies as high as I can get them within the configured power band, with the differences that come in basically being a function of just variation in silicon quality that you get from like a big batch? Which is to say, there can be some differences if you're AMD and you make 10,000 parts. All 10,000 parts don't respond to, say, 200 watts of TDP equivalently. They'll respond close, but some will actually do better than others. I would recommend using the power setting. The reason why I say it as follows is most people, most people will like to get, it doesn't hurt. You're not lowering the floor in order, in some jobs to raise the floor on others. You're just raising the floor opportunistically, right? And most people are happy to take essentially free performance, even if it only benefits some of the jobs that they run. If you run an MPI workload, it isn't that big a deal, because in MPI, as a general matter, you're going to be governed by your slowest performer anyway. So even if some cores are running a little bit fast, in one server are running faster than cores in another server, it won't make too big of a difference. You'll run, your MPI job will run more or less in line with whatever the slowest performer is. So as a general matter, I would recommend determinism mode set to power. I know it sounds weird to say that power is actually the one that can give the best performance. Meanwhile, there's a performance mode. Think of a better way to say these are probably common lowest denominator performance versus opportunistic performance determinism. C states, like a lot of you who've been, say setting up servers for a long time, you probably, for a decade or more, you've been like, oh yeah, first thing you do, go into the BIOS for HPC, disable C states. On the way these processes evolve, it's a long story. Trust me, just enable C states. It's fine. And it will give you actually your best frequencies as well for scenarios where you want to drop cores and get more frequency to a smaller number of cores that your individual job will run. Preferred IO, go set this to any IO device that is your most important PCIe attached device, whether it's an SSD or something else. In our case, and for a lot of people in HPC, that's going to be your high performance network interface. On Rome Milan, you can only set preferred IO to be a single device. So in other words, you can't say, logical question, why can't I just set preferred IO to be all of my devices? My two local NVMe devices, my GPUs, some things like that. You can only set preferred IO to be one thing. The one where it makes actually the biggest difference is it won't really make a difference on GPU. So don't worry about using it on your GPU. Where it really helps is in latencies for an InfiniBand NIC. So TLDR, just set preferred IO to be your InfiniBand NIC, or like your Slingshot NIC if you have like a Cray system or what have you. Set that to be your preferred IO device. There's another setting called LCLOK, LCLK for that PCIe device. Set that value to 593. It might show up as 600 or 593, but it's really 593 under the hood. What 593 means, don't worry, doesn't matter. Just know you want to set it to that, and that will give you better network card latencies. Simultaneous multi-threading. Oversimplified version, that's AMD's term for what you probably know as hyperthreading on the Intel side. Enabled equals 2 threads per core, disabled equals 1 thread per core. I'm not going to make a recommendation here simply because what makes the most sense is very workload or scenario dependent. On Azure, we disable it because the vast majority of applications that customers are running for HPC want it disabled, and some applications actually go backward in performance just because that many additional threads tends to overtax certain global shared assets like GMI links, like I mentioned before. But do whatever makes sense for you. That's perfectly fine. One thing I can tell you is that the benefits of SMT are less on the Milan side than they are on Rome. What SMT really is it's essentially spare space in the execution pipeline of a processor that the IPC of the physical core can't consume. So it's a way of essentially using up that remaining space in the execution pipeline. Because Milan is materially higher, about 20% higher IPC than Rome, but there's less leftover space in the execution pipeline on Milan than there is on Rome. So the benefits all up on Milan tend to be a little bit less than they are on Rome. So take that for what you will, depending on which processor you are either planning to buy or already have bought, and you're tuning BIOS settings and that kind of thing. And then the last two I would tell you about are CTDP and package power limit. These are very important ones as well. These are hard governors you can set in your BIOS to say, I never want my processor to go above this level, or I want it to go down to this level. So all EPYC processors, they have a number that's associated on the box, like 225 watts, 180 watts, 200 watts, 155 watts. But then usually, almost always, that processor actually has a configurable range. You should play around with that to find what's the sweet spot for your application. A lot of applications, especially say something that's, if you're running a lot of workloads that are purely memory bandwidth bound, or you're running something that's really big at scale and your workload becomes communications bound, throwing a bunch of additional power at your processor doesn't actually get you anything in the way of application performance. For instance, if you were to say, what's the difference between a 7742 application or a Rome CPU, which runs at 225 to 240 watts, and a 7H12, which is a 280 watt Rome, same 64 core part, but now you have 40 to 55 watts more worth of power. It gets you a little bit more frequency if you have a problem that's super compute bound. It'll give you a better HPL score, but if you're running a bunch of like memory bandwidth applications, it's not really going to get you anything extra because you were already able to saturate all the memory bandwidth from the cores in the first place. So take a look at, you may be able to reduce your power draw quite a bit just by playing with these two settings. Think of, and by the way, what's the difference between CTDP and package power limit? Think of CTDP as like the warning sign to your processor or to your CPU socket or your motherboard to stop in terms of how much power it gives to the processor. Package power limit, though, that's the real boss. Your CPU won't draw more power than whatever you set in package power limit. So you can set those values differently. You can say, CTDP 225, package power limit 240, and it will actually, it might even go a little bit above, 225, but also no more than 240. But if you set PPL at the same value as CTDP, then it'll stop right at PPL. PPL is the one that really, really matters. For those of us for whom power is a significant driver in the OpEx costs of running our entire end-to-end HPC environment, this is a very material setting because you can save a lot on your OpEx costs just by turning power down in order to find the right sort of sweet spot in terms of performance per watt for your workload. There are a million additional resources that you could go look up. Everything I'm sharing today it's coming from like data that either we've shared or data that you could go readily find for yourself. So I'm just pointing to you to existing reference data. One particularly good data set or sort of presentation I would point you to is this one right here, is the where it says AMD presentation to NASA. This was just given by a gentleman, a great guy at AMD named Jason Hogan O'Neill, who's one of their HPC leads. He's got a bunch of deep dive data and information that you should go look at that goes into some of the things I've talked about even in greater depth. I'd also go point you to the recommended tuning guides for HPC scenarios that AMD has published. Azure, we try to share what we know with the community as a member of the HPC community. And so you'll see a number of Azure blog posts. Again, not putting them there as advertisements, but more as here's reference data you can go look at to help set your expectations, get a view of how different kinds of EPYC perform on different kinds of workloads, that kind of thing. And there's, again, many, many more resources you could go look at to help you figure out, does EPYC make sense for you for the kinds of problems you're trying to solve, how best to use it, how does Rome look like versus Milan? How did EPYC even become a big deal in the HPC space to begin with? Those sorts of things. And that's all I've got for today. So thank you to everyone. Happy to take any feedback that folks have. I hope this was useful, but I'd love to hear from folks about how I can make it even more useful, how we in Microsoft can make this kind of discussion, our learnings more useful for the broader HPC community, and happy to take any questions.
Thank you very much, Evan. This was excellent. We do have a couple of questions. If anyone wants to raise their question themselves in the Zoom session, please raise your hand and we'll let you do so. We'll start with a question from Bennett Fauber from the University of Michigan. I don't think he's in the Zoom session, so I'll raise the question myself. About half our workload on the cluster is now serial or low core count on one node. Have you noticed the configuration should differ for that as distinct from small or large MPI workloads?
Good question. So we see a lot of those applications. So a lot of the applications that I showed you here today were things that are sort of, let's call it, fairly recognizable within the HPC community. You know, workloads from what's called the multi-physics space. We have a lot of customer workloads that run ensembles of serial applications, like financial services, for example, that they'll run big ensemble sweeps of single core jobs. The best advice I can give you, if you essentially want to, if you think about EPYC, or if the way you think about any server you buy, including EPYC as, I've got a bunch of serial tasks and I want to essentially bin pack them on servers as efficiently as possible. The first is that if there's serial tasks, if they're not memory bandwidth bound, then you've just got a bunch of ensemble sort of high throughput compute. Then just laying out processes, as I mentioned at the beginning, where you start to load them. As you load them up, you're doing it not by going from one to the first core to the second core to the third core. Go from the first core on the first CCD to the first core on the second CCD to the first core on the third CCD, all the way to the last CCD. Then go back to the first CCD and continue to increment that way all over again. Do it that way. The reason why you would do that is that way you're always providing a balanced subdivision of global shared assets to each individual task. That's one. The second thing I would say is, let's pretend the scenario you're describing is, I've got lots of relatively small jobs that run at low core counts, serial or lightly threaded. I'll use a lightly threaded example. And I really just want to get max perf to those scenarios. So I'm going to make up a scenario that kind of illustrates what I'm talking about. Let's say you run a lot of 16 core CFD jobs, something like that. In that case, you are going to be able to soak all the memory bandwidth from an EPYC processor with a 8-core part or a 16-core part. You don't need to go to the 32, 48, 64 core parts. And so you can save probably a lot of money and get the vast majority of the peak performance just by buying a lower core count part that still, like I said, is able to consume all those global shared assets that are actually the real drivers of your application.
And maybe a short follow-up, which also popped up in the Slack chat, in terms of assigning those single core workloads to different CCDs as they are filling up the node. Do you know if Slurm is, or can you configure Slurm to do that for you? Because that, and for most HPC sites, it's going to be Slurm that's going to be assigning the cores to individual jobs.
That's a good question. So I'm with the big asterisk that I'm not 100% sure about this, but I'm 95, 98, 99% sure. The answer is yes. The reason I say that is because there's a whole other team in Azure who runs the software and services side. There's a gentleman by the name of Rob Futrick and another gentleman by the name of Andy Howard, who if that person wants to contact me or reach out to EasyBuild and get connected, happy to connect them with. But we support a lot of folks running Slurm on top of Azure who are running the exact style use case. And I believe that was an issue initially with things like high core count EPYCs back in the early days of Rome, but I think it's long been since addressed. But I couldn't tell you the exact details, like best practices of how to do that with Slurm. My guess is that we've got a blog post already published where Slurm does somewhere happy to take that as a follow-up for this group.
All right, excellent. So next up is Chris Etzel.
Evan, thanks. You touched on it towards the end of your talk in the section on the BIOS settings.
Mm-hmm.
And even earlier when you were talking about the power cap that various facilities face, but mainly in the context of OpEx. And I'm thinking with the recent release of the IPCC's sixth assessment report on global climate change and the necessity to reduce the amount of CO2 emissions, can you comment on the relative energy efficiency of different Azure VM types for typical HPC workloads? So say I was in one particular Azure location so that the green energy balance is the same and the time of the day is the same. Which VM should I choose if I wanted to minimize CO2 emissions? And how would I tell?
Oh, that's a great question. It's one that comes up a lot now. People want to understand how am I being, let's call it carbon efficient, with my HPC. There isn't a simple answer. I'll do my best to give the best nuanced answer I can. As a general matter, start from the premise of the HPC optimized instances, be they from the CPU-based compute or the GPU compute or even our FPGA compute. Broadly speaking, those are optimized for what you'd broadly call the community of HPC class workloads, which is to say that they will be significantly more performant and performance efficient than the VMs you see from Azure's general purpose compute line of VMs. So I'll use Azure as a specific example here. So we have things called like the F series or the D series or the E series. I'm not going to get into too many details, but think of that. Those are all those are the high volume VMs that people in Azure use for a million different kinds of IT use cases. They're designed to be Swiss Army knives, whereas HPC infrastructure is designed to be a scalpel, right? Focused efficacy. Under the assumption that you've got in your question, that you've got let's call it a canonical HPC application, you are definitely going to get the most carbon efficient performance from using one of the HPC optimized instances from which would be the H series, the ND series, the NC series, or the NP series, which is the FPGA compute. That's smaller volume, but we still have customers doing those kinds of things. That's the simplest way. One feature, it's funny you bring that up. One thing, I think an increasing customer request, we don't have this yet, is customers they almost want to see like in their Azure dashboard, like how many carbon credits did I use? Like a recurring thing so they can keep track of that. I don't think we have that yet, but in terms of just, if you wanted to know what's the most performance per watt efficient instances we have, and use that as a guideline for, is that generally going to provide the best, the most efficient use of carbon and energy-based assets, it will be our HPC assets. The oversimplified version, if I were to say like just pick one thing and as a general rule, it will be your most power efficient thing would be the HBv3s with Milan, just because Milan's kind of like the best HPC processor out there right now.
Cool, thanks. And +1 for the visibility to end users. I think that would be great. Cheers.
Yeah, sure.
Okay, another question from Justin, which I'll raise here. To what extent is maturity of software, like for linear algebra libraries, as a concern for AMD? For example, in the performance plot that you've shown, was it harder to achieve peak performance for AMD systems than it was for Intel systems?
Great question. No, there's as a general matter at this point now, there's not that big of a difference. There's no sort of, I would say, additional difficulty. Usually when we run into difficulty, to be honest, most of the time it comes from the commercial software side, where for a variety of reasons, a commercial software vendor tends to have, let's call it, less forward inertia to keep their software modernized in step with the latest hardware. So I'll give you an example. We were working with a company in the energy space that was running a seismic processing application. And that vendor had really last coded their application probably 4 or 5 years ago, which is not atypical. And the software simply freaked out at anything more than, I think it was like 8 or 16 NUMA domains in the server. They just had no idea how to deal with that. And so we had to go talk with the vendor and explain to them like, hey, this is a thing called EPYC, and you should probably, like, a lot of your customers are using it and we're using it, and you should, you know, modernize your code for it. And they did, and it wasn't a significant effort. It's things like that. It's less like the hardcore library stuff. Where we see library stuff come up is more like MKL dependencies. And usually there it's less a, you know, was it difficult to start using Bliss or something like that? It's more like we're talking with the customer who still is using like a older, you know, some very old version of you know, software application X. And the modern version of that software application has had great support for EPYC for a while, but the customer for one reason is like, yeah, you know, we still use the version from 2011. It's like, okay, yeah, I'm not surprised that, you know, your software that was last tuned for Sandy Bridge isn't super well optimized for stuff today. And there it's less an issue of like, you know, is it actually hard to use the modernized code? And the barrier is more like, does the organization, getting the organization to go, okay, I guess we're gonna make the change and we're gonna start rolling out the newer version across the organization, and we're gonna validate it for our use cases and those kinds of things. But in terms of the actual, you know, are the software libraries on the AMD side any less suitable? No, they're pretty darn robust. We don't have any problems. If you throw a given application at us right now, and we just sort of throw it at Rome and Milan instinctively, you know, unless there's, like I said, some like oddball legacy requirement in terms of like versioning. As a general matter, I'm at this point, we're not gonna expect to see, you know, major differences in terms of the difficulty to achieve peak performance between, you know, EPYC and Xeon. As long as you follow the best practices, I would say the library thing doesn't matter nearly as much as be aware of, like I said, it's not just one big monolithic block of cores. Don't say, yep, just use all the cores and hope for the best performance. Lay out your processes based on the physical topology of the processor, in much the same way that, you know, for those of us who have ever run very, very large scale jobs, like if you've ever gotten a research grant to go run on some gigantic Cray system, and someone tells you at a certain point, like there's asymmetry in terms of network connectivity, and here's where there's the best bisection of bandwidth, and here's where there's oversubscription, and you need to start thinking about how the physical layout of the network, you essentially bring that down to the CPU level. And like I said, AMD is early there, but all CPU vendors are kind of have to go in this direction eventually.
That ties well together with the question I had. So you mentioned that you get a question from Azure customers often to minimize the amount of stuff they have to learn in order to use the fancy stuff and get good performance. Mm-hmm. How do you combine that with having to learn things like don't use all the cores, or make sure you map out your processes well if you want to get good performance? That sort of disagrees with each other, I think. Is there tooling that helps people to realize that they're doing the wrong thing and that guides them in the right direction? Or
so I would say that's a really great question. There is I would say, so this almost gets to the central thrust of our roles, whether it's in Azure, whether it's you or anyone else in the audience who supports a broader set of users, in terms of your value in the overall value chain, which is a lot of it is sort of being a Sherpa, a guide, you know, a teacher for these users. A lot of what we take is what I consistently find to be effective is teach the people who are running the HPC operations at the organization X what things they should teach to their users. Because a lot of the times when the best way to scale awareness, and most importantly, a change in behavior to users, is to teach the people who will be on the front lines. I think there's this often assumption that if you're going to do HPC in the cloud, that the users just come flooding to the cloud directly. And I mean, someone can, and let's say it doesn't happen often. That's one of the great things probably about the cloud, is that, and anyone's cloud, it's not an Azure statement, is that any individual user can just sign up, get on, and go do something directly. But as a general matter, if I'm talking with, let's call it big company X, and I'm talking with their HPC team, the role they end up playing with respect to their users in terms of walking that balance of, here's the newer hardware here, and here I'm gonna put a carrot out there for you in terms of, here's the great performance you can get, but you as the user need to be aware of, let's call it, these 3 or 4 things. That role doesn't really change whether someone is buying infrastructure to put on premises or they're using Azure in the back end. To the end user, whether the infrastructure lived on site or in Azure is sort of like transparent to them. They have no earthly idea. It doesn't matter to them. They're just a user. They're just submitting things. What we really try to do is focus on, how do we educate the people who will be on the front lines with the users, who not only know the users, know the personalities of the users. They know the workloads of the users. They know what's called the business sensitive or the time sensitivities, of the individual user teams, and just go through the same exercise you always have, which is engage with those groups, understand what they're really trying to solve for, and then just provide them the key, let's sort of, top 5 principles, top 5 things to do. And then with illustrative data that supports what you're saying. The degree to which you can simplify it, like, here are the 3 to 5 things you got to know. Here's some key data point that really illustrates what I'm describing to you in action. Usually if you do that, then it gets absorbed by any reasonable HPC person, and what we find is they tend to have success passing it on to their end users and their customers as well.
There's not like a key metric that we can essentially raise a red flag on if they're massively overloading on bandwidth, and they could be getting better performance by using half the cores or whatever.
I think there are rules of thumb. Like I said, there's certain things. So remember before when I said a funky core count, more cores is not necessarily better. If you see someone running some number of cores for their job that is not, that does not represent like that you can look at and go right away know that there's load imbalance on the CCDs, that's a good first order indicator. They're probably not doing the best thing by their application. Right. So one is just, looking at the number of tasks or something. That's one. In terms of a memory bandwidth bound application, a lot of it depends on how performance sensitive your users are and the scale that they're running at. So as an example, let's take CFD. You gave CFD as an example. A 64 core, a sweet spot will be using 64 cores out of a max of 128 in a Rome or a Milan system. It will give you close to, but not as much performance as using all the cores in the system. You still get incrementally more performance. If everyone is running, if you bought a bunch of 128 core nodes or a bunch of 96 core nodes, you may find for a bunch of exclusively 1 VM jobs that, yeah, you get significant sort of declines in performance efficiency by using all the cores, but you're running a bunch of 1 node jobs, so therefore it's fine. It's just max performance and go use all the cores. But if you're going to run, let's say, CFD jobs, and you're going to see a big scale, a spectrum of scale. Some people run 1 node jobs, some people run 128 node jobs. Then I would say it's good to pick a rule of thumb that you can sort of teach everyone and just say, stick to this. It'll always give you the best or close to the best performance, like just use 64 cores, just use, half the cores per CCD. And the users will generally be fine and happy. There might be 5, 10, 15% more they could get. And if you have users who are super sensitive to that, because let's say they pay for very expensive software licensing that would make them rationally incentivized to go do that. Okay, fine, then maybe that scenario doesn't work. But as a general matter, if you're running a memory bandwidth bound application, use half the cores per CCD and don't think about it. So in the Rome generation, that would mean you buy the EPYC 7542 processor. And in the Milan generation, that'd be like saying buy the 7543 or the 7F43, I think it's called. I think those are all sort of the high end parts that have all the CCDs. So it's got all the fully populated quadrants, the best possible memory bandwidth, and it just basically they fuse off half the cores per CCD.
Okay, we have one more question if you still have time for it, by Robert Schade, if he's still in the Zoom meeting. If you want to raise your question yourself, Robert, you can. You should be able to unmute yourself, and if not, I can raise it for you. So the question was, which aspects would you focus on, or would you recommend to focus on for a data center when they are migrating their users from a Skylake SP system to a Milan system?
What aspect to focus on? From an end user standpoint, is that your understanding of the question?
Yeah, for migrating their users, yeah.
Is the question essentially presuming that the decision to, this isn't the scenario where it's deciding whether to buy Milan to migrate customers to?
That's probably a done deal. Yeah.
Got it. It's a done deal. So I would say my oversimplified version would be this, which is if you get the following three things. If you do three things, you'll be good. Let's cover the first 80-90% of it. The first is, to an individual user, is your application memory bandwidth bound or is it more compute bound? That's one. Oversimplified, if it's more compute bound, use more of the cores. If it's more memory bandwidth bound, use half or a quarter of the cores. That's the simple guidance right there. The second piece I would guide you on is identify the relevant level of scale. Because with Milan, as I showed you before, Milan's superpower is its advantage over all prior technologies. I showed you Rome earlier, but the same holds true on Skylake, is Milan gets better with scale. So understand what level of scale, or so what the curve is of your application, because it may actually, you may consume a higher percentage of what's called a shared pool of infrastructure by running at larger scale, but you also may get super linear speed up from doing so, and therefore consume that for a shorter amount of time.
Okay. Yeah, I think that makes a lot of sense.
That's right. Yeah, and the third thing I would say is,
yeah, was the third one.
The third one is make them, show your users, show them a big blown up picture of the physical topology of like how show them it like a die shot and be like, you need to think of these processors as regions of cores. Allocate your processes, load balance them across these regions, and you'll be fine. If they nail those three things, is your application compute bound or memory bound? What's the relevant level of scale for you? And have a basic understanding of the topology and how to use it, you'll be good.
The last one is a challenge, and we've briefly discussed that. I mean, for a lot of our users, we have to tell them, don't blindly request all the cores if you're running single core jobs, because it's not going to help you. Like it's not magic, but going from that to telling them, use half the cores and make sure you spread them well across the node. That's potentially a big jump, and that's not a criticism on AMD itself. I mean, it's clear we're going the chiplet way, even with other vendors. So I guess there's tooling missing, or it's not just explaining to the users, but we need tooling to make this automatic as well, because user support doesn't scale with 1,000 users. If you have 1,000 users, you cannot keep saying the same thing and keep teaching the new PhD students coming in. I mean, for the next 20 years, we cannot keep doing that. So we need tooling around that does it for us.
Yeah, no, I get that. There's a certain, generally with users, it's not like, most sites, there's not like an even distribution of, let's call it user expertise. Usually have a handful of users who really actually know infrastructure principles really well. And you've got a long tail of users who know almost nothing about infrastructure. They're a scientist or an engineer, and they've been taught how to submit an application, and get a result back, but that's, kind of it. I can't give one, I would say, firm, the simplest thing, if you're trying to, let's call it, get a material, I'll use a worst case scenario. Let's say you wanted to involve absolutely no additional understanding for your users. And as a consequence of that, you are willing to take some hit to the top end performance that you can deliver. You still get performance benefits over Skylake. To be clear, you can get substantial performance benefits over Skylake, but you really, really can't educate a bunch of users. That's a scenario where you might want to consider something like NPS equals 1, L3 as NUMA disabled. Because there you're just going to make every socket look to the operating system and application like it's a big monolithic die, like all dies, including AMD's before EPYC, have ever been. And will you probably see some weirdness, at times? Yeah. Is that the absolute best performance scenario you can give to your customers? No, but if in the big picture of things, you're minimizing user education pain is ultimately kind of the most important thing, while still moving the ball forward for your users in terms of performance and performance throughput. That can be a perfectly rational decision to do something like that.
Does that mean you're essentially handing over the placement of processes to the BIOS itself, and it tries to do a smart thing, or it's just totally stupid and it assigns things sequentially?
You're not handing over to the BIOS. You're more handing over to the operating system and to your application
kernel. Yeah.
Yeah, that's exactly right. What I will say is, and so this is probably a very effective. This now dovetails into another controversial area. The most modern OSs have a better, both on the Linux and the Windows side. And believe you me, I understand, like probably most of you aren't running Windows HPC. We actually have a lot, you see a lot like financial services, they run all of their stuff in Windows because their core application they build their scalable apps from is all Excel. A lot of rendering applications are done in Windows. So we see both, but whether you're talking about Windows, but obviously overwhelmingly Linux, the newer versions of Linux have much better kernel support to understand the physical topologies and capabilities of the modern processors. Which is to say, and I realize this is causing folks to cringe, if you can use like a CentOS 8.x or a RHEL 8.x, it will be more performant and smarter about how to use Milan than will CentOS or RHEL 6 or 7.x. There could be we've seen as a general matter about a 10% performance uplift on a lot of applications, going from even the latest CentOS 7.x builds that we maintain and optimize to like CentOS 8.1, 8.3, things of that nature. So the way to reduce performance variability and weirdness is use the modern OSs, which is keep your, as a general principle, keep the software stack, whether it's the applications or the operating system, as in line with the generation of hardware that you're deploying into your infrastructure. Don't fall into the trap of running legacy software on top of modern hardware.
Yeah, that's something we try to pay a lot of attention to in the EasyBuild community as well. Yeah, keep up with recent stuff. And maybe one last one to wrap up. Sure. So a follow-up on something you've mentioned several times. So Maxime's question is, so you're saying if it's memory bandwidth limited, use half of the cores, but what does that mean in a shared environment where jobs are flying around and Slurm is assigning cores to jobs and you don't really know what's going to happen. Or if you're even going to be landing on a single socket or your job is going to be spread over multiple sockets. So, and what about in a scenario like this? How careful should you be? Or
so in a, how careful should you be? So number one, Slurm has plenty of controls these days to determine things like, am I going to allow job multi-tenancy per server, right? So there's no sort of table stakes assumption that you have to support multiple jobs per server. So if your concern is, I've got a memory bandwidth sensitive application, I don't want jitter from sort of resource contention, Slurm provides plenty of controls to avoid that. But let's assume for the sake of our—
Just to quickly interrupt you, with the core counts per server going up, it's actually becoming less and less interesting to go with the single node configuration, because then either you're using the whole node even if you're running a single core, and that doesn't make a lot of sense.
Correct, but like I said, it's important, don't over-index on the number of cores in the same way that don't over-index on— we as a community have been routinized to think of the relevant level of scale as, oh, I'm scaling my job by cores. You were never scaling your job by cores. You're always scaling it by a balance of all the global shared assets you're consuming, right? So it's like, you know, someone said like, well, you know, in your example, you know, I don't want to use only, you know, a small handful of cores in a large core count machine. Like, are you also freaking out if you're only using 10% of the memory of the server? So do the thing that makes the most sense for the performance needs of your job. And if you're an IT admin, then, you know, there's certainly this next level conversation, which is, do we want to, at an organizational level, is it beneficial to support job multi-tenancy? Once you start supporting job multi-tenancy, then you're running into a lot of the same things that we deal with on the cloud on like general purpose VMs, where you get this tremendous density advantage. You can pack a ton of stuff into the server and it will run, it will complete, it will, you know, good stuff. But the flip side is, yeah, you are going to have resource contention. Yeah, whether it's Slurm or a hypervisor is going to make imperfect decisions in terms of where it places processes, because it's just trying to put things down as efficiently as it can. And it doesn't have an awareness as to, like, you know, how sensitive to memory bandwidth is this kernel versus that kernel. It doesn't know those sorts of things. So the first order, I would say, the first question I would say, is with Slurm, if you have a memory bandwidth sensitive application, if there's no requirement to support multiple jobs per server, then I don't think you're going to have a real challenge. It's just a matter of, you know, submit the job, configure Slurm, or at the job level, how to load processes in the load balance ways that I was advising before. If you're getting into scenarios where now you're talking about having to do like job multi-tenancy, then I would say, I can't give you one piece of guidance, because a lot of it may depend on how sensitive you all as an organization or how an individual user might be to the scenario in which their job runs, their job completes, but job to job runs will have variation in performance, or jobs may run slower than they otherwise could. If you're an organization where, you know, you have users who go, I need to submit a bunch of jobs and I just need them done by next, 2 weeks from Friday now. And if they get done sooner than that, great, but it doesn't really do anything for me because I can't really do anything with the data until next Friday anyway. Like, that's a scenario where you go, okay, yeah, maybe I can, pack more jobs in from a density standpoint. But if you have customers who are going, say, I need this stuff that's back as fast as possible, then maybe that isn't something you want to be doing.
Yeah, and Maxime is following up on that one, and we should wrap up. And I think the point of view from Azure compared to a physical HPC center is maybe very different there. But yeah, it's a good discussion to have over a couple of beers, I think. Yeah. I mean, yeah. To be honest, we see both. We have customers who do both sets of scenarios where they want to tightly, they want to submit a bunch of jobs. Usually,
the folks who want to submit jobs that where they're packing a bunch of workloads in with Slurm onto a single server, those tend to be sort of serial or lightly threaded scenarios, not the memory bandwidth sensitive stuff. But we do see those as well. And then we see folks who are like, nope, I want peak performance. So we see the full spectrum. If it's, there isn't one bit of guidance here. If it sounds like I'm hedging, it's simply because I don't know the particular sensitivity of organization X or user Y. It really comes down to the sensitivities of the individual user in the organization.
Yeah, and the mix of workloads and types of users is very big even for individual HPC centers as well. So even there,
yeah, exactly.
They probably don't know. I know.
Yeah, exactly. I mean, you're going to have cases where the most important thing is keeping this one or two users super happy, and you just want to give them the red carpet treatment, and nope, no VM multi-tenant CPU. You get fully dedicated nodes, and you have other customer scenarios where you're thinking about where you're going. Our job is to drive aggregate computational science throughput for our organization. And yeah, that may slow down an individual user here or there, but as long as that's the right thing for us to do at an organization level, then that's how we should base our node packing policies. That can be a valid view too. There's big diversity there.
Yeah, exactly. All right. Okay, I think we should wrap up here. We're hitting close to the 2-hour mark. So thanks a lot for your time, Evan.
You're most welcome.
And we'll see about looking into maybe a follow-up part in a couple of weeks or a couple of months. We'll probably send out a short survey to the people who registered and see how well they like the talk, and if it will make sense to have a part 2 that goes a bit more in depth, perhaps.
Thank you again for inviting me. It was fun to do this. I hope this was useful for folks in sort of whatever HPC scenarios they have going on, and special thanks to all the folks in the parts of the world where it's getting into the evening hours. Thanks for sticking with me.
Yeah. Thank you very much for your time. Thanks a lot.
Thank you.
Okay.